In 1998, the web was large enough to be useful and chaotic enough to be nearly unusable. Search engines existed, but finding reliable information through them required patience and luck. Most results were cluttered with irrelevant pages and ranked by criteria that had almost no relationship to actual quality. The tools available were not failing because the engineers building them were incompetent. They were failing because the underlying assumptions about how to rank web pages were fundamentally wrong, and nobody had yet figured out what to replace those assumptions with. Two Stanford graduate students did. What Larry Page and Sergey Brin built starting in 1996 was not an incremental improvement on the existing approach. It was a different theory of the problem, applied at a scale no search engine had attempted before. Understanding how Google won requires understanding not just the algorithm they invented, but the engineering culture that made it practical. The problem with keyword counting and what replaced it, every major search engine in the mid-1990s operated on a version of the same model. Count how often a search term appeared on a given page, factor in its position in the document and the title, and rank results accordingly. Yahoo, AltaVista, Lycos, and Excite all built on variations of this premise. The approach had a specific weakness that the web made catastrophic. If rankings were determined by keyword frequency, then anyone who wanted higher rankings could simply repeat their target keywords. Websites discovered that invisible text the same color as the background in pages stuffed with thousands of repetitions of popular search terms could both push a page to the top of results without any relationship to what the page actually contained. By the late 1990s, search results for many competitive queries were dominated by pages created specifically to game the ranking system rather than to provide information. The major search engines attempted countermeasures, but each countermeasure created a new avenue for manipulation because the underlying model could never distinguish between a page that was genuinely about a topic and a page designed to appear that way. Pages, in Brin's insight, was to move the source of authority outside the page itself. They asked what academic publishing already knew. When researchers want to determine whether a paper is significant, they do not count how many times the paper's keywords appear in its text. They look at how many other papers cite it, and they weight those citations by the significance of the citing papers. A paper cited by 10 leading researchers in a field is more significant than a paper cited by 50 graduate students. The prestige of the source matters as much as the count. They called this PageRank, named after Larry Page, and applied the same logic to hyperlinks across the web. A link from a page that itself had many high-quality links pointing to it was worth more than a link from an obscure page nobody referenced. Instead of measuring what a page said about itself, PageRank measured what the rest of the web said about it. The manipulation problem did not disappear entirely, but it became dramatically harder because building a network of authoritative links required either genuine reputation or elaborate coordination that left detectable patterns. Their original research project at Stanford, called Backrub, was specifically a crawler and analysis system designed to map the link structure of the web. The Google search engine was built on top of that foundation. The name Backrub referred to the backlink analysis at the core of the project. When they incorporated Google in September 1998, the search index already covered around 25 million pages, which was a fraction of the web but enough to demonstrate that the ranking approach produced results qualitatively different from anything else available. Why the engineering was as important as the algorithm, the PageRank theory was elegant and, once explained, relatively straightforward to understand. Making it work at web scale was a different problem entirely. Calculating PageRank requires knowing the link structure of the entire web simultaneously, because the rank of any given page depends on the ranks of all the pages that link to it, extending recursively across billions of documents. The computation is iterative. You run the calculation repeatedly, using each round's output as the next round's input, until the rankings stabilize. This requires storing an enormous link graph and processing it with high efficiency, while the web itself continues to change. Page and Brin had minimal funding during the early years of the project. Enterprise servers with the storage and computing capacity to handle web-scale data were prohibitively expensive. Their solution was to build their own servers from commodity PC components, writing custom software to coordinate hundreds of cheap machines that individually were unreliable but collectively produced stable, fault-tolerant computation. The approach anticipated what would later become the standard architecture for distributed computing at scale. At the time, the idea that serious computing infrastructure could be built from off-the-shelf consumer hardware, managed by software designed to work around individual machine failures, was not widely accepted in industry. Speed was treated as a core product requirement rather than a secondary concern. The Google homepage launched with a nearly empty interface, a search box, and 2 buttons. Loading it took a fraction of a second on the connections available in the late 1990s. Competitors had moved toward portal-style homepages packed with news links, advertisements, weather widgets, and other content intended to keep users on the site as long as possible. Google's design reflected a different theory. Users wanted answers quickly and would return to a tool that consistently delivered them, not to a tool that tried to hold their attention on the way to an answer. The speed investment extended to the back end. Google's infrastructure was engineered to return results within a few hundred milliseconds, which required precise attention to how queries were processed, how indexes were structured, and how network traffic between servers was managed. The anti-spam engineering was continuous from the beginning. Because PageRank made link manipulation more effective than keyword manipulation, the incentive shifted toward acquiring links rather than stuffing keywords. Google built systems to detect coordinated linking schemes, low-quality link farms, and pages that appeared authoritative in the link graph but provided no genuine content. The spam detection work was never finished. It evolved as manipulation strategies evolved, and treating it as an ongoing engineering problem rather than a solved one was itself a significant competitive advantage. The outcome of the competition and why the gap widened. By 2002, Google had established a clear lead in search quality that was apparent to users without requiring any technical knowledge. You could run the same query on Google and on any competitor, and the difference in the usefulness of results was obvious. This quality gap was the product of years of accumulated engineering decisions, each of which was individually defensible, but whose combination produced an infrastructure that competitors could not replicate quickly. Yahoo had an opportunity to acquire Google in approximately 2002 and declined, reportedly because the asking price, which was reported at the time in the range of $3 billion, was considered too high for a company whose primary product was a search engine without a clear advertising revenue model. Within a few years, Google had developed AdWords, the auction-based advertising system that placed text advertisements alongside search results based on the specific queries users were running. The targeting precision this allowed, combined with the scale of Google's search traffic, produced revenues that made the declined acquisition price look negligible. Microsoft recognized the threat early and attempted to build competitive search technology through MSN Search. Later rebranded as Windows Live Search and eventually as Bing. The effort required years of investment and never succeeded in closing the quality gap in organic search results. Despite Microsoft's substantial resources and its ability to run its search engine as a default in the Windows operating system and Internet Explorer browser. The crawling infrastructure, the ranking systems, the spam detection, and the index freshness that Google had developed over years represented a compounding advantage that could not be closed by spending money on the same problem in the same way. Microsoft needed a different approach to the problem, and building one from scratch while Google continued to improve was effectively impossible. Google did not win because it had a single breakthrough advantage. It won because its approach to engineering treated each component of the problem: the crawling, the indexing, the ranking, the speed, the anti-spam work, and the infrastructure as problems worth solving at a high level of rigor, and it maintained that standard consistently over years while the web grew from tens of millions of pages to tens of billions. The competitors who tried to copy Google's ranking approach discovered that the ranking algorithm alone was not the advantage. The advantage was the entire engineering system that made the ranking approach work reliably and quickly at web scale. If this breakdown of how Google's engineering approach built an enduring technical advantage helped clarify what actually happened in the early search engine competition, hit like Subscribe for more deep dives into the engineering decisions behind major technology outcomes, and drop a comment with which aspect of Google's early technical strategy you think was most decisive.